So today, what we're going to be talking about is a tool called InspireCast. My name is Sean Bentley. I've been with GoEngineer and formerly with Desai Solutions, a reseller for SolidWorks, and related products as well, for about 13 years now. My primary roles with Desai and with GoEngineer are to do typically technical support, a lot of training, and also webinars like this and other online content. So I'm a simulation specialist, so I've been specializing in the simulation side of the software. That includes the structural analysis, fluid dynamics, flow simulation, plastic injection molding, and so on. But today what we'll be talking about is this tool called InspireCast. On the agenda for today, or general outline of what we'll be covering in this presentation, first of all, we'll talk briefly about what is InspireCast. Okay, just generally what does it do. Then I'll do a quick demonstration, just show you, kind of walk you through a quick and dirty study, and I'll go ahead and let it run as well. And while it's running, we'll take a look at a few other little details about InspireCast, such as the different kinds of components and processes for metal casting that it supports. Then hopefully by the end of that review, we'll be able to take a look at the results from our run, or I can pull something out of the oven and show you. And finally, I'll show you how we can include a few extra components and try to improve the casting that we do our initial run on by adding things like chillers and risers and so on. And then finally, there'll be some time for some Q&A at the end of the webinar. So what is InspireCast? InspireCast is a fast, easy, accurate, and affordable simulator for early casting feasibility and process development. It's a tool that allows you to do metal casting, so aluminum and steel for the most part, and be able to incorporate all sorts of different components to run trial and error tests. So why do customers choose InspireCast? Well, it gives designers quick feasibility assessment on some of their existing designs. They're able to see, is this part going to be castable? Am I making this region too thick? Should I be worried about things like porosity? It reduces a lot of the trial and error required with trying to produce high quality castings. You can do a lot of the trial and error right inside the software rather than physically making castings and then having to tweak them and to try to get a good casting out of it. And finally, one of the big reasons to choose InspireCast over some of the other metal casting softwares out there is it's got such a quick ramp up time. It's very easy to use, and that's what I hope to demonstrate as well in this webinar. So inside of InspireCast, it includes some simple geometry creation tools. Here, for example, you see our riser creation tool, where we can do one click to create many of these risers, as well as put sleeves over top of them. So you have access to a variety of different casting components that I'll sort of give you an overview of that we can create in pretty much a single click for almost any of these. Then it has a lot of customizability. You'll be able to understand, I think, the interface pretty quickly. The general setup for a casting process inside of InspireCast looks something like this. First, we start out by importing your design into our casting tool, which I'll show you in a moment. Then we identify which parts of your design are the casting part. We tell it where the gates are going to be located. Then we tell it where other components are. If you've already drawn in your risers in SolidWorks, if you've already drawn them and you want to import it into InspireCast, you'll be able to recognize those components as risers in InspireCast or create them in one click. Then we'll define what the casting process is going to be, whether or not it's going to be just a basic setup or a gravity fed or a high pressure or low pressure casting. And then finally, once we're done with those 4 steps, we'll run our casting analysis. And we'll be able to see all sorts of different types of results after we run the analysis. We'll see things like the temperature when it's filling. We'll be able to view things like how much porosity might be inside the part after it solidifies. So we'll see results from a couple different categories, one from the filling phase and another from the solidification phase. So using these results, you'll be able to pick out regions like this region here that has high porosity, and we'd be able to try to correct for some of these defects. by either adding risers or making design changes. So I guess without further ado, let's walk through some of the process with you here. So I'm going to basically walk through these general steps that I already outlined in some of my earlier slides. So here's the part I'll be demonstrating InspireCast on. So many of you might recognize this component. It's for the brakes in your car. So what I'm going to do is just see how well we can cast this part and see if we have any design issues with it. So in order to set up a casting simulation, I've already drawn this model, as you can see, in like a tool like SolidWorks or a 3D CAD package, and I've brought it into our InspireCast tool. And inside of InspireCast, I can do things like simplify some regions that I don't plan on including in the actual casting simulation. With the Simplify Geometry tool, I can just remove a few of these holes, just a single click, 1 and 2. Then also, if I move over to the casting interface, you can see here's where those 5 steps that I'll walk through are. So I'm going to start off by defining the casting part. In this case, I'm going to make this thing out of steel, but you can see this library has a whole bunch of different materials that we can incorporate. And this is actually relatively new. They keep adding to this tool with each iteration of it. So the fact that we can customize some of this library is actually a nice new feature that we've added lately. But I'll make this part out of steel. I'll use this 3310 with this initial temperature. After I define the part to be casted, then next I'll tell it where the gates are going to be located. I'm going to test out a gate right in the top here. I wonder how if I just drill a hole through my casting and have it fill downward. And that reminds me too, I do need to define the gravity direction as well, make sure it does go downward. This is the direction that my casting is going to be oriented. You can imagine where that parting line is going to be sitting. And then next what we'll do is tell it a few extra components here. If I define, let's see, I've got a core I need to do right in this center here. So I'll tell it it's made out of silica sand. So that'll have a lower thermal conductivity, so the heat transfer through there won't be as fast as if it was going through like an aluminum block. But also the mold itself, since this is a steel part, I want to make sure I make my mold out of something that can withstand the high temperatures, the melting temperatures of steel. So we'll use green sand for the mold. All right, and just like that, that's sort of at a bare minimum of what you need to do to set up a casting simulation. At this point, I can use maybe some of the default conditions for the basic setup that I have here. Just tell it to use a default initial velocity. It's about 1 meter per second. That'll pour in through this injection location here. And we can run a simulation. I'll run both a filling and a solidification analysis. So that does take a few minutes to run. And while that's going, and you can see we can run multiple simulations simultaneously. While that simulation is going, let me give you a bit of an overview of the casting interface and give you a sense of some of the other things we can do with it. So first of all, I showed you a couple of components that we can set up in InspireCast. I showed you a core, but and I've kind of talked about risers and so on. But to sort of summarize the different types of components that you can include in InspireCast, like I mentioned before, risers, and you can also include sleeves to insulate those risers. And those can be insulated or exothermic, where they can actually react and generate heat to further sort of insulate, create an even better insulation on those riser components. Other components that you can include in your castings, and I'll show you one of these later, a chiller. So we can put chillers on our casting blocks to try to instigate a direction of cooling. So we can try to make sure it cools in a particular direction to try to eliminate porous regions that might otherwise occur out in these regions. You can add overflows. So you can kind of see in this example, these overflows will help with if you have air entrapment. The overflow allows the air to get trapped in the overflow region instead. So That way you end up having a defect on the overflow region rather than on your actual cast part. So these can also be added in a single click. Then also on your mold block, we define that mold, and I showed defining the a green sand mold in this case, and I showed defining a core. But you can also include coolers inside of your mold block. So these cooling lines, so that way you can test out different cooling patterns to try to improve your casting. Now also there's different types of ways we can set up the basic casting process as well. In this case, I just showed you the basic setup, okay, which is just gives me a quick general casting. But we also have things like gravity, which can be used for the sand casting and die casting, high pressure for die casting, and also a low pressure die casting setting as well. So I'll show you some animations that illustrate these 4 different processes. So the basic setup is kind of like what I'm illustrating with this this first study. Okay, here you tell it either a fill time or a velocity, but either way, what it'll do, even if you do key in a fill time, it'll solve for the velocity based on the total volume that it has to fill. So it really, if you use basic setup, you're really just telling it the velocity at that injection location. If you select gravity process, you have all sorts of options here, but a few of them boil down to velocities in a way. If you select filling time, it's the same as using the basic setup, or flow rate also, kilograms per second, it'll solve for the velocity based on that. But a few of them are a little more sophisticated. Here, this tilt pouring option, we can use the gravity with tilt pouring to fill a casting in this way. Then high pressure. If we use the high pressure setting, here you can see the piston. We're pushing the piston forward to fill this cavity. And then here you see the pressure profile that we're defining here. Well, really it's a length versus velocity profile. As we move the piston, we're telling it how fast the piston moves. That's how we're controlling the fill rate through this curve. And then finally, low pressure. If you want to fill a casting using the low pressure setting, here we define a time versus pressure curve to tell it how it's going to fill that cavity up. Okay. So if you need to do any of these 4 basic processes, and sort of what it boils down to though is you need to define the velocity on that inlet. There's a bunch of different ways to define that velocity. You can define it using these 4 different processes. All right, so let's check on our simulation and see how it's going. So here's the simulation I ran a moment ago. It looks like it's already done with the filling phase, and now it's moved on to the solidification phase. So while it's still running, we can view some of the results, kind of see how it's going. So one of the results I'll take a look at is just the fill pattern. Now, using these tools on the right here, it's easy to adjust the temperature min and max. Right now you see the whole thing's red because I have the minimum set down to all the way down to like the mold temperature right now. But let me bump that up to like say 1750. That way we'll see some color. So here you can see the filling pattern and also the temperatures as it's filling it too. Let me set this to loop as well. So that way we can just kind of see some of the issues with it potentially here. So I think I'm not too sure if I like this location. You see how it fills around here. We might have a lot of erosion. Our mold might erode a lot in this region. Let me go ahead and pause this and kind of backtrack over this area. So you can kind of see that initial filling pattern there. And we have a lot of turbulence down here too. Okay, and that can cause all sorts of issues with the mold as well. Okay, further erosion down in the bottom. So what I'd like to do, let's take a look at a few of the other results here. For example, velocity. Sometimes it's helpful to see where those high velocities are, where we can see there's maybe more mold erosion. And also directly just a mold erosion plot. And here I'll customize the min and max so we can again see a little bit of color. So it looks like, yeah, right in those regions I was a little worried about. That's where we see the highest erosion. But overall, it's not too bad. We're looking at this is the velocity near those walls here. It's looking like about 500 millimeters or half a meter per second. Okay. Now, other results we can take a look at are some of the solidification results. And while I was viewing these results, I can the solidification study got done running. So let me move on to that. So you can kind of see the initial filling pattern here. And then here you see the mold. So here you see the mold And in this one, let's look at solid fraction. So we'll see some interesting things here. This is how it's solidifying versus time. So you can see the regions that solidify first, or the outer part of that shell, of course, the regions that are contacting the mold body, of course, those solidify the quickest. And then inside it eventually solidifies, and you can see right here and over here, I get these two separated regions. Let me slow it down for the webinar here so we can kind of see those right about here. We get these two separate regions that solidify, or three rather, here, here, and here. And since these solidify last and they're sort of inside the molded part, they're kind of nestled inside of it, we might expect to see some porosity inside of there. And then as a matter of fact, if I go to my porosity result, and again, to show some color here, maybe set it like this here for a moment. You can see those are the same regions where I have some porosity due to shrinkage. So those are a few of the key results I wanted to show you. There's also a lot of other results we can kind of flip through and look at, but for this design, these are some of the big ones. So let's see if we can make some improvements to this design. So what I'm going to do is we're going to go back into the casting process here, and we're going to set up a few extra components to try to help improve the casting, see if we can reduce these porous regions. So one of the things I'm going to do, if we go back to the components, since I saw a big porous region here and here, I think what we could really use is a couple of risers. So if I put a riser here, I'm hoping that'll be close enough to where when it solidifies, it's gonna kind of keep feeding, the riser will keep feeding the molten material into this region, and we'll be able to see the porosity ends up here instead of here. So in order to add risers, if I go to this component section, just a single click on where I want to put the riser. How about right about here? Okay. I can adjust some of the dimensions of it. Maybe I'll round down the modulus here to 0.5. And I want to make it a little bit taller as well. So I'll just drag this thing upward a bit. Maybe 25 millimeter. Let's try that out. Nice big riser. Now I want to put the same riser on the other side. So in order to get some symmetry out of this, I might as well mirror this thing over. So I can go back to some of my geometry modeling tools and just create a mirrored version of that. And now also to help these risers too is if I add some sleeves to them, that'll give them some insulation. You can test it without sleeves and with, these runs are pretty quick to where you'll be able to do all sorts of experiments with it. But for now, if I just add sleeves onto these two here and here, and I'll make them exothermal as well, as spare no expense. We're gonna use the sleeve type that's going to actually generate heat as well. That'll keep those risers nice and warm. So they'll be the last region to solidify. Now another thing that might help too is if I had a chiller. If I had a chiller to this side of my mold, that'll I'm hoping that'll take the region that was porous here and make it cool a lot faster, and maybe it'll hook up over here, and we'll end up getting rid of the porosity on this side. So that'll kind of give a nice directional cooling. So in order to add a chiller, it's just another one-click component. If I use a chiller block, I'll put it right in the middle of this. Give it a couple of dimensions. I'll make it, let's make it 20 tall, how about? Okay. And let's see, let's move this thing a little bit this way as well, just a couple millimeters or so. And you can kind of see too, with the way these the way these one-click components work, it overlaps that geometry. And if you've run any structural analysis in SolidWorks simulation, for example, on the SolidWorks end, you know that it doesn't like overlapping geometry. But in this tool, the way it handles these overlapping geometries is it automatically does some combine features, some Boolean operations. It'll automatically subtract one body from another. It prefers the casting body. That's the high priority. It'll subtract from other bodies to get the right size and shape of these. So it automatically does a lot of that Boolean work in the background. Now, one other thing, in order to, we bumped into an issue on the front here where, or in the top here, where we had a bit of a remote erosion, and I was worried about some of the turbulence. So I'm going to change this injection location. We're going to shift that around maybe to the back side here. maybe put it lower. How about this region here? So well, sometimes what it's good to do, instead of just placing the injection location right on the surface, if I actually draw a portion of the runner, that'll give a more natural inflow into this region rather than putting the injection right on that face. So I'll draw a simple runner system right inside of here as well. So I'll put a just a couple millimeter diameter. We're going to use 8 millimeter for the opening. And I can use some of the geometry modeling tools directly inside of InspireCast. We don't have to go to our SolidWorks modeler or other CAD modeler to do this. And I can just simply drag things. It works kind of like SolidWorks' Instant 3D, if you've ever used that. And I'm going to revolve this guy around an axis. Let's call that 90 degrees this way. And finally, I'll put a little extra extrusion on the top of that. Let's pull that straight up. And some arbitrary, doesn't have to go too high. I just want a portion of this so that I get a more natural flow coming into here. Okay. So finally, I'll identify this as my runner system. And I'll tell InspireCast that the injection is going to be right here up on the top of this runner system. That's where it's going to be pouring in. That's where the velocity is going to be. It's going to come in through there and then naturally flow into this casting. All right, so let's see what all these improvements did. So at this point, I would go ahead and run this again, but just like the last one, it does take a few minutes. It takes about 5 to 10 minutes. So rather than wait for that one to run, I'm going to pull this one out of the oven and show you what the results look like. We'll do a little comparison. So I think it's going to be this guy here, or I guess we'll see. Yep. So here's already one that's been pre-run. Change the animation here. Kind of play that back. See, I don't get as much turbulence it didn't look like in the beginning there. Let's see. Let me pause it and kind of show just the beginning part of this flow. So it kind of flows over there, and I'm expecting to see a bit of erosion in the bottom of my mold now, but hopefully not as bad as what we saw on the sides there. A more natural place to fill it anyway. Then fill it all the way up to the top. It fills those risers all the way up. Now, really the key result I want to look at here for comparison to see if we've made some improvements on is this solidification. So let me go right to that step and see how that looks. And I'm hoping to see those risers are last to solidify. And all right, that didn't look too bad. Let me play it back and kind of drag through this region here. So this time you can see there's a little bit of a disconnect there. So that chiller helped out quite a bit, but it's still a little bit. But on the other side, it looks like for the most part, it's cooling from left to right. Looks like that chiller probably helped out quite a bit there. And then also you see it does disconnect from the riser. So maybe we might need to do some other design tweaks to try to help with that. On the right side, it doesn't look as bad. But let's see how does the porosity compare? So if I go back to my porosity plot, and just so we're doing apples to apples, change these to some of the same kind of settings I had a minute ago. Here's the porosity I have this time around. Just one little speck there. So yeah, still a little bit of room for improvement, but it's a lot better after we added some of those components. All right, so ultimately, here was sort of the before and after picture. I made it a little more sensitive. I made these images a little more sensitive than the image I just showed you, but you can see kind of the same general result before I added those extra components versus after. So to wrap up, oh, by the way, yeah, we do also have access to all sorts of other results. Some of the ones that I looked at for today, though, were these ones. Okay, temperature, velocity, mold erosion, solid fraction, and porosity. But if you're curious about, do we have NIAMA or microporosity, pipe shrinkage? Yeah, those are also results that we can look at, but I'm not trying to make a whole comprehensive tutorial in this one little webinar here, okay? But if you have questions regarding any of these, feel free to let us know. So to wrap up, customers choose InspireCast because it gives designers feedback on feasibility on their designs. They're able to bring in their designs into InspireCast, run quick tests. You saw in just a few minutes from start to finish, I was able to completely run a study think over the course of 5 minutes or so, we were able to run a study and get some quick feedback on our casting results. And ideally, this will create a situation where you have to do a lot less trial and error, a lot less troubleshooting after you have actually created the mold and try your first cast run, and have to make a bunch of tweaks to it. If you use InspireCast before you go through all that, it can help to reduce the amount of troubleshooting required later on down the road. And plus, it's a very quick ramp up time. Hopefully, in just this short little webinar, you've seen kind of almost how to use the tool from start to finish. You've got a sense of how easy it can be.